Hello, my name is Sekiyama, Division of Materials Physics, Graduate School of Engineering Science, Osaka University, Japan. In this movie, at first, the complex refractive index is introduced, which directly determines the optical property of solids. This index is a kind of consequence of the interaction between the charged particle, electron in most cases in solids, and incident light, classically described as electromagnetic waves. On the other hand, the electric function representing the response of materials to external electromagnetic field is also introduced, and its relation means a relation between the complex refractive index and the electric function is explained. Please enjoy this movie.
Let me start from the situation in this figure, where a solid materials occupy the area of Z is positive, namely the plus Z area, and the plane wave light is coming along the plus Z direction from the minus infinity. The electric field of the incident light is expressed as this formula. After the light is coming, some portion of the lights are reflected as schematically shown here. It should be noted that the sign of the wave number of the electric field of the reflected light is flipped, since its propagation direction is along the minus Z direction. Here, the amplitude of the electric field are defined as a complex number as EI tilde or ER tilde, and very observable electric fields are real part of the overall function. The light intensity is proportional to the square of the absolute value of the amplitude of the electric field. This is also the consequence of the pointing vector of the electromagnetic field. In the case of the incident light, the intensity is shown by the square of EI tilde. On the other hand, the other portions of the incident light are transmitted with absorption. You can imagine that the light in solid is still going on, but gradually absorbed by solid as a function of travel length Z. In order to describe the gradually absorbed light in the solid, the complex refractive number n tilde is introduced. The real part, n, stands for the widely used refractive index, while the imaginary part, kappa, represents the degree of absorption of the light in the solid. Then the electric field of the transmitted light is expressed by this formula, where n tilde is inserted in the kz term. In other words, the wave number k is replaced by n tilde k. Even in the solid, the angular frequency is conserved. You can notice that the photon energy of the light itself is unchanged before and after going to the solid. Now we can calculate the intensity of the transmitted light following to the definition. Since the complex refractive index is complex scalar, we can obtain this formula. The component of the exponential inkz minus omega t stand for the plane wave. And therefore, we can regard this part et tilde times the real exponential function as amplitude as a function of z. Then the intensity is evaluated as this formula. You can find that intensity is reduced on going to plus z direction while describing the realistic situation. Here, I introduce another physical quantity, alpha, called as absorption coefficient. This quantity is directly observable one since we can obtain by the measurement of intensity as a function of z. From this formula, we learned that coefficient alpha is expressed by 2 kappa omega over c like this. Since the wave number is modified between vacuum and solid, but the angular frequency is not changed, both alpha and kappa should be represented by the function of angular frequency or photon energy. In this case, as shown in this figure, the incident angle is 0, called as normal incident condition. Of course, the amplitude EI tilde, ER tilde, and ET tilde are not mutually independent following to the classical electromagnetism. By calculating normal reflectance at the incident angle of 0, the ball of complex refractive index is revealed. For obtaining the normal reflectance, we also need to note the magnetic field of light, usually called as P, in other words, the magnetic flux density. The magnetic field of the incident light in vacuum are easily obtained following by this formula. Also in solid, the Maxwell equation representing the Faraday's law of induction is satisfied. Therefore, the magnetic field of the transmitted light is expressed as this one. Since the propagation direction is opposite for the reflected light, the sign of its magnetic field is flipped. Then we need to take the boundary conditions at the solid surface of z equals 0 into account for deriving the reflectance. In this case, x and y components of electric field must be continuous as a function of z. Since all the electric field of the incident, reflected, and transmitted light are along the x direction, this relation is satisfied from the boundary condition. On the other hand, the magnetic permeability mu is almost the same as that in vacuum mu0, even for the solid when omega is away from 0, which will be discussed later. Then the magnetic field B becomes also continuous at the boundary z equal to 0 along the x and y direction parallel to the surface plane. Therefore, we get the relation of the magnetic field and finally obtain this one. From these two equations, we obtain the amplitude ER tilde and ET tilde as a function of EI tilde and complex refractive index N tilde, as shown here. Since the intensity of the light represented by the square of the amplitude, a very observable quantity of the normal reflectance, large R, is obtained as this formula. We can notice that the normal reflectance, large R, is a function of only complex refractive index. For nearly transparent materials, the real part N is nearly 1 and imaginary part kappa is nearly 0, which leads to the normal reflectance of nearly 0. On the other hand, even if the real part is nearly 1, the normal reflectance becomes larger when kappa is larger. When the incident angle theta is deviated from 0 from the normal incident condition, the calculation becomes rather complicated and we need to take the difference in the polarization into account. At first, I start from the S or sigma polarization, where the electric field of the light is perpendicular to the scattering plane. In this figure, every electric field is perpendicular to the z-axis and surface normal. For both polarization, the Snell's law determining the refraction angle theta prime is the same, n sine theta prime equals to the sine theta. Here, n stands for the real part of the complex refractive index. This law tells us that refraction angle theta prime is lower than the incident angle theta if n is larger than 1. Also, the other formula of the reflectivity are basically similar to those for the real number refractive index with imaginary part kappa of 0. We obtain the formula by replacing n by n tilde as shown in this formula. The observable reflectance is expressed by this formula as a function of theta, theta prime, n, and kappa. As shown in the next slide, the reflectance in the S polarization increases with increasing theta. For the P or pi polarization, the electric field of the light are not perpendicular to the z-axis as well as the surface normal. So I forget to say, but this plane is a scattering plane. So you can notice that for the S polarization, the electric field is perpendicular to the scattering plane. In the case of the P polarization, the electric field of the light are within the scattering plane. Therefore, the formula derived from the boundary condition are changed from those in the S polarization. Due to this difference, the reflectivity is modified, where the theta and theta prime are interchanged in the formula for the S polarization. This situation is basically the same as that for the kappa of 0. Then we get the observable reflectance as shown in this formula. It is rather difficult to notice, but the reflectance in the P polarization once decreases when theta ongoing from 0 degree. Although it depends on kappa, but the reflectivity takes a minimum near the so-called blue star angle, evaluated as arctangent n. After the blue star angle, ongoing from the blue star angle, the reflectance increases and approaches to 1 near theta of 90 degrees in the very grazing condition. These graphs show the simulation of the incident angle dependence of the reflectance for different real number refractive indices assuming kappa of 0, rather unrealistic parameters. The solid line stands for the reflectance in the S polarization, whereas the dashed or dotted line represents the reflectance in the P polarization. As I said before, the reflectance increases monotonically with the incident angle theta for the S polarization. On the other hand, for the P polarization, the reflectance decreases up to the blue star angle, defined as arctangent n. At which the reflectance becomes 0 if kappa is 0. The reflectance is higher for the S polarization than for the P polarization, except for the theta of 0 and 90 degrees. I showed the other simulation including the realistic value with n is less than 1, but the kappa not equal to 0 as shown here. The left graph shows the angle dependence of the reflectivity with n of nearly 0.3. As kappa increases, the reflectance at 0 degree increases. the minimum reflectance angle, effective blue star angle, is shifted to the higher incident angle with increasing kappa. These realistic complex refractive indices are realized for the UV region with a wavelength of 100 to 250 nanometer, as shown like this, for indium, for silicon, and for magnesium. Another characteristic phenomenon at n is less than 1 is total reflection. This happens when there are no solution for the theta prime refraction angle for the Snell's law, where the sine theta over n is larger than 1. In this situation with kappa of 0, the light cannot be going into the solid and all components of the light are reflected. When kappa is finite, some portion of the incident light are absorbed on the solid surface, but still reflectance becomes larger, as shown here. For example, for the real part n of 0.98, nearly 1, the reflectance is very lower than 10% up to the incident angle of 70 degrees. However, when theta is larger than 80 degrees in the total reflectance region, the reflectance rapidly increases. These are just optical properties, results of the interaction between the incident light and charged particle in solid. From the next slide, I show how the complex refraction index are related to the electromagnetism. In order to understand the relation between the complex refractive index and electromagnetism, we need to start from the Maxwell equation and material shown here. Since in the steady state, the materials are charge neutral, we can set the charge density in the materials rho is 0. Furthermore, for simplicity, we assume that permittivity epsilon and permeability mu are scalar. These assumptions are valid when the material has no anisotropy, while the epsilon and mu are expressed by tensors for the anisotropic materials. Further, we assume that Ohm's law is held. The current is proportional to the applied electric field with the coefficient of conductivity small sigma, meaning that incident light intensity is weak enough not to change the nature of materials by the incident light. Using these assumptions, Maxwell equation can be rewritten without using the charge displacement d, the other magnetic field h, and current density in the material J as those formula. So we can replace J by using the Ohm's law like this. Then further using the identity of the vector calculus, we obtained partial differential equation for the electric field as shown here. This is for the material, so the transmitted light introduced before must satisfy this equation. So by putting this electric field into the above equation, we can obtain this relation. After the calculation, we obtain the relation of n cubed square as this form. Using the relation between the frequency and wave number and that among the speed of light, vacuum permittivity epsilon 0 and vacuum permeability mu 0 shown here, n tilde square is expressed like this. For non-magnetic material with mu equal to mu 0, this approximation is mostly available even for the magnetic material since mu is deviated from mu 0 only when omega of 0 and mu is nearly mu 0 for high frequency omega as explained in the next slide. Then we get the relation between the complex refractive index and so-called dielectric function epsilon tilde defined as epsilon 1 plus I epsilon 2. Here, the real part of the dielectric function stands for the charge polarization, which is the same as that for the static case of omega of 0. For the imaginary part of the dielectric function, its numerator represents electric conductivity called as optical conductivity, showing how the current is seen by the electric field of light. Usually, the dielectric function is expressed as a function of angular frequency omega, namely equivalent quantity to the photon energy. Therefore, the complex refractive index n tilde is expressed as the square root of the dielectric function epsilon tilde is also a function of angular frequency. Then the real and imaginary parts of the complex refractive index n and kappa are obtained as this formula as a function of the real and imaginary part of the dielectric function epsilon 1 and epsilon 2. This is a relation between the complex refraction index and dielectric function. So this one, complex refractive index, stands for the optical nature of the material. On the other hand, the epsilon tilde stands for the electromagnetic nature of the material. By this formula, these two natures is mutually related. So far, I said that the permeability mu in the materials can be approximated as in vacuum mu0. This is just by considering which effect, electric or magnetic effect, are dominant by the incident light in materials. These are expressions of the electric and magnetic field of the monochromatic plane wave light. The importance is the fact that the amplitude of the magnetic field B is E0 over C, where E0 stands for the amplitude of the electric field E. Then we consider the classical force F acting on the charged particle moving with the velocity v. These are from the Coulomb force by the electric field and the Lorentz force by the magnetic field. Since the amplitude of the magnetic field of the light is E0 over C, the term V times B is evaluated as the order of V over C times E0. This means the ratio of the effect of the magnetic field of the light to that of the electric field is roughly V over C, which is much smaller than 1, when the velocity is far from the speed of light c. In this case, we can neglect the Lorentz force as well as the effect of the magnetic field. In most electrons and ions in solid, their velocities are far from the speed of light. Therefore, we can neglect the effect of the magnetic field of light. This is valid for the classical and semi-classical treatment where the light is assumed to be classical electromagnetic wave. As shown in the later lecture, effect of the magnetic field is taken into account after the light vector potential is quantized. So far, I have introduced the complex refraction index n tilde, a very important optical index. This optical index is directly related to the electromagnetic quantity, the electric function epsilon tilde equaling to the square of n tilde, as I discussed before. On the other hand, These real and imaginary parts are not mutually independent. Not mutually independent. The complex dielectric function satisfies the so-called Kramers-Kronig relation derived from the causality as I explained from this slide. To discuss the mathematical nature of electromagnetic fields, we consider the time dependence of the electric field E and electric displacement field D in the materials. The electric field E and electric displacement field D as a real function of time t are expressed by using the inverse Fourier transform of E and D as complex function of frequency omega or photon energy as these formulas. Here, the normalization factor 1 over 2 pi is omitted since this is just a constant and does not affect the discussion here. Further, we suppose that the electric displacement D is expressed as the combination of the electric field E and the dielectric function epsilon tilde. Of course, both electric field and electric displacement field D must be real vector function of time t. In order to satisfy this condition, since cosine omega is an even function of the angular frequency omega, while sine omega t is an odd function of the angular frequency omega, while the imaginary part of the Fourier transform must be an odd function of angular frequency omega. That means the Fourier transform equal to its conjugate with putting minus omega. This nature is applied both electric field E and displacement field D. Since the Fourier transform of the displacement field D is expressed as a dielectric function epsilon tilde times the Fourier transform of the electric field E times permittivity in vacuum epsilon 0. Therefore, the dielectric function epsilon tilde has the same relation as that of the electric and displacement field E and D. Namely, the real part epsilon 1 is an even function of the angular frequency omega, while the imaginary part epsilon 2 is an odd function of the angular frequency omega. According to the electromagnetism, the displacement field D is also a result of charge polarization P. Here, the dielectric function is assumed to be isotropic. Therefore, the Fourier transform of the charge polarization P is proportional to the Fourier transform of the electric field E, where we can define another complex function of the angular frequency omega as chi tilde, which equal to the dielectric function minus 1. The complex function chi tilde is called as a complex electric susceptibility or complex charge susceptibility. The charge polarization as a function of time t is of course expressed as the inverse Fourier transform and further expressed as this formula. On the other hand, the polarization P as a function of time t is a result of the time evolution of the path response to the applied electric field in the past time, which means the causality. Therefore, by using a certain real function z as a function of time tau, the polarization P is also expressed like this. When the electric field E in the past time t minus tau is expressed by the inverse Fourier transform, we get this formula. Then we change the order of integration. This formula is obtained. Here, function g as a function of time tau originally represents how to respond to the applied field, which is a real function. Comparing this formula and this formula, we can recognize that complex electric susceptibility chi-tilde is a Fourier transform of the real function z. In order to know the mathematical nature of the dielectric function epsilon tilde and electric susceptibility chi-tilde, once we expand chi-tilde as a complex function of the complex frequency omega tilde of omega 1 plus I omega 2 as shown here, then this expanded function chi-tilde is expressed like this. Since the function g is a real function, the real part of the chi-tilde is represented by this form, and imaginary part is shown by this form. Then we consider the derivative of the real part. Derivative of the real part by omega 1 is calculated as like this. Since omega 1 appears only here, we can also get the derivative of the imaginary part of the omega 2 since omega 2 appeared here. For the derivative of the real part by omega 2, where the result is shown here, which is the same as minus of the derivative of the imaginary part by omega 1. These relations are equivalent to the Cauchy-Riemann equations, which guarantees the holomorphic nature of the complex function in complex analysis. Therefore, we expand the electric susceptibility chi-tilde is holomorphic at the positive imaginary part plane. Then we consider the integral of chi-tilde over omega tilde minus real number omega 0 along the closed path C, as shown in this figure, where the singular point omega tilde of omega 0 on the real axis is avoided. Since this function is holomorphic on the boundary and inside the integral path C, the integral becomes 0. Furthermore, the integral along the large half circle with radius of infinity also becomes 0. Then we get this relation. Here the second term stands for the integral along the clockwise direction in the vicinity of the singular point expressed by the residue times minus I pi. This result means that the real part is expressed by the integral along the real axis of the imaginary part divided by omega prime minus omega, while the imaginary part is expressed by the minus of the integral of the real part divided by omega prime minus omega. This is known as Kramers-Kronig relations derived from the causality expressed using the dielectric function as these formulas. These Kramers-Kronig relations are often seen in other fields in physics because these reflect the causality in the physical quantities. Now we get the Kramers-Kronig relation as these forms. However, it is not practical because the integral should be performed from minus infinity to plus infinity, while the observable angular frequency is positive. Therefore, further considerations are needed to derive the practical forms. Before going to the integral only for positive omega, the integral is divided like this. Further, we can write this formula as this form when we set omega 2 prime as minus omega prime in the first term. Then the two integrals can be merged again as this form because epsilon 2 is an odd function of frequency. Finally, we get the form with integral by frequency from 0 to plus infinity like this. Also for epsilon2, we can calculate at the same manner as above and obtain this result. Because epsilon1 is an even function of the angular frequency omega, then we get this final result. So the Kramers-Kronig relations are written as practical form like these.